go over some of the rules for drawing ray diagrams with converging lenses. So I've drawn an object here, drawn my lens. I've got F, the focal point, and 2F labeled on both sides because it's a piece of glass, it's see-through, so it's kind of symmetric on both sides. A lot of these rules are going to seem really familiar. They're kind of like what goes on with mirrors, except with mirrors, when the light bounces off of the boundary, whereas with lenses, we're looking at refraction as the light's passing through. So that's kind of one key difference, but there are certainly a lot of similarities between converging lenses and converging mirrors. So what I've got here is an object, and I want to locate the image for that object and also be able to say a few things about the image properties. Is it right side up? Is it upside down? Is it bigger? Is it smaller? Is it the same size? Is it real? Is it virtual? All those kind of characteristics. You could probably do that with math really easily by just using the equation that you're familiar with from mirrors, whereas F is the distance F to the middle of the lens, DO is the distance of the object to the middle lens, and DI is where the image is from its location to the middle of the lens. That's the math part, but I want to go over the rules for actually drawing the pictures. Rule number 1 says that any light that enters parallel to its principal axis is going to pass through the lens and then end up passing through this F on the other side. So rule number 1, light that goes in parallel passes through the lens and then through the far F, the far away F, meaning the F on the other side, so the far focal point. And so I'm just going to take the light from the top of the object that fits this and draw that in. Of course, light from this top of the object goes every which way. Right now, I just want to draw the beam of light that happens to go parallel to this black line. So let me show you what I mean by rule number 1. Here comes light in parallel. And there is a boundary where it's going to bend. And of course, there's another boundary where it's going to bend. To simplify it, we just show the refraction happening right in the middle. Of course, that's not actually what happens. It happens at both boundaries. It's easiest just to change directions right in the middle there. And after it goes to the lens, it's got to pass through that far away F. So there's rule number 1. In parallel, it goes through the far away F. Now you can imagine if light can go one way, it could take the reverse path. Meaning if it happens to come in through F, it's going to go out parallel. In fact, that's our second rule. We're going to send light in through F, and I should really say in through the close F, the close focal point, and the result is that it's going to come out parallel. So let's do that one together. Start with the light from the top of this object that happens to go through that close F. And I'll draw that line. And right at the middle there, I'll pass the light through, keeping it parallel to the starting line and show where it ends up. But just from 2 beams of light only, I can already identify the image location, but I'll give you a third rule just to help you confirm. I think already you can see that the light meets right here. So that's where the top of the image is going to be. So the image looks something like this. It's upside down relative to the object. It happens to be smaller relative to the object, and it's between F and 2F. And all those characteristics are going to depend on where that object is placed, but in this case it's inverted, smaller, and between F and 2F. We can also say it's a real image in this case, because the light really does meet up there. Had these lines not converged but diverged, then we'd have to dash them back and look for a virtual image. Because the light really meets there, that's a real image. Now that we know where the image is, that means that any light that comes from the top of this object and hits this lens is going to reassemble right there. I mean, literally any light. If it goes up, it's got to end up there. If it goes down, it's got to end up there. So we can actually take a look and see, well, what is kind of the straightest path for light to go on? can see that that line that I've just drawn passes right through that middle point right there, right through that green dot. And so that's a nice little confirmation rule if you want to do a third rule to make sure you can find the images. The confirmation rule says that light that goes in through this, I guess I'll call it the midpoint of the lens, in through the middle of lens, doesn't really bend, keeps going straight through the lens. So of course you don't really need 3 rules to find the image. If you have 2 rules, you'll be able to see where the image is, but the third is a nice confirmation that it fits with what you found from your first 2. So rule 1, in parallel, out through the far F. Rule 2, in through the close F, out parallel. And rule 3, just straight on through the middle. And where they intersect, there's a real image. Or if they diverge, just dash them backward and see where the virtual image is. And of course, you can confirm mathematically that that image is where you expect it to be.